Assalamu alaikum. Today we'll be reviewing some selected questions from May 24, Unit 1. Um, so we start with question number 3A. It says, what is the molecular formula of limonene? So there are two ways to approach this question. There are two ways you can approach this question. One way is to simply find out the molecular formula. So what you can do is you can count the number of carbon atoms here. If you count the number of carbon atoms here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now counting the number of carbon atoms was unnecessary because all the options have 10 carbon atoms. So it was really unnecessary to count the number of carbon atoms, right? So what you could do is you could simply count the number of hydrogen atoms. If you count the number of hydrogen atoms here, if you look here, if you look at this carbon here, this carbon has only one bond that you can see, right? There is only one visible bond. So the other three are hydrogen atoms. So there are 3 hydrogen atoms on this carbon. If you look at this carbon, there are 1, 2, 3, 4 visible bonds. If there are 4 visible bonds, there is no hydrogen atom here. If you look at this carbon here, there are 2 visible bonds here. So the number of hydrogen bonds will also, number of hydrogen atoms will also be 2, right? So if you count the number of hydrogen here, so the number of hydrogen here is 3, the number of hydrogen here is 2, then the number of hydrogen atom here is also 2, then there's 0 here, then there's 1 here, 2 here, 1 here, 3 here, 0 here, and you have 2 hydrogen atoms here, right? If you add them up, that is 3, 2, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16. So B should be your answer. Then B should be your answer. It is C10H16, right? Now there's another way you can determine the formula. Is that there are 10 carbon atoms, right? So what you do is you write the formula of the alkane. Another way of finding the answer is that you write the formula of the alkane with 10 carbon atoms. Alkane is C10H22. This is the formula of an alkane, right? Now what we see here, there is a cyclic structure here. So you must remember that one cyclic structure results in the loss of 2 hydrogen atoms, right? One cyclic structure results in the loss of 2 hydrogen atoms. So you subtract 1 H2 for the cyclic structure. For the cyclic structure, you subtract 1 H2. Okay. Now there are 2 double bonds here. Now if there are 2 double bonds here, for one double bond, you have to subtract another H2. Because whenever a double bond is formed, the 2 hydrogen atoms are lost, right? 2 hydrogen atoms will get lost if one double bond is introduced in the molecule. So there are 2 double bonds here. For that, you subtract 2 hydrogen molecules. In total, you subtract 6 hydrogen molecules from the formula of the alkane. So now if you subtract 3 hydrogen molecules from the formula of the alkane, it comes out to be C10H16. This would be your final answer. Okay, we'll move on to the next question. Next question, question number B. It says, limonene is completely hydrogenated in the presence of a nickel catalyst. Okay, this was completely hydrogenated. Now, if limonene was completely hydrogenated, it becomes a cycloalkane, right? It becomes a cycloalkane. What is the empirical formula of the compound formed? Now, if this is completely hydrogenated, see this compound, we remove the numbers here. Now, this compound limonene, if you look at limonene, it has 2 double bonds. Limonene has 2 double bonds, right? So if you saturate it completely, the double bonds will not be there. If the double bonds aren't there, then the formula of limonene will now be C10H16, and you add 2 moles of hydrogen here. Why? Because in order to get saturated, there must be addition of 4 hydrogen atoms, right? When it gets saturated, the double bonds won't be there, and 4 hydrogen atoms will be added. So what you do is you add 4 hydrogen atoms here. If you add 4 hydrogen atoms here, what happens? The formula comes out to be C10H20. Now if you find the empirical formula for C10H20, so the formula would now be CH2. So the answer to question number B will be D. Alright. Now we move on to the next question. It says, what is the electronic configuration of a chromium 3 ion? Now the chromium 3 ion, if you look at the chromium 3 ion, now the element chromium has a slightly different electronic configuration. If you want to write the electronic configuration of chromium has atomic number 24. It has the electronic configuration argon 4s1 3d5, or you can also write 3d5 4s1. Both of them are correct. You can write any one of them. So it has the electronic configuration 4s1 3d5. So now if it loses 3 electrons, you must remember that electrons are always lost from the 4s orbitals first and then from 3d. So 3 electrons, so the first electron will be removed from the 4s, so it becomes 4s0. 2 electrons will be lost from the d subshell, so this would become 3d3. So your answer would be argon 3d3. Argon 3d3 is option B. Alright. If you have any questions, you can always write in the comment section. Yeah. Then we move to question number 13. Question number 13 says, what is observed when iron 3 carbonate reacts with ethanoic acid? Since it is a carbonate, and since it's an acid, right, it will give you effervescence. It's going to give you effervescence, right? Because it's a carbonate and it's an acid. When you react a carbonate with an acid, the reaction would give off carbon dioxide gas, and due to that you will see some effervescence. Now since it's a solution of iron 2, since iron 2 carbonate reacts with ethanoic acid, forms a solution of iron 2, the solution of iron 2 will be green. So it would be green solution along with effervescence. So the answer to question number 13 will be C. C will be the answer. Yeah. Alright. Then we move on to section B. Section B, I think you asked for question number, what question is this? Question number 16. Section number 16, it's about silicon. And I think you asked in the mass spectrum, there is a small peak at m/z equal to 14. And where did this small peak or this small signal come from? So it's a mass spectrum of silicon, right? Since it's a mass spectrum of silicon, now silicon has a mass of 28, right? Silicon has a mass of 28. Now if there is a peak at m/z equal to 14, it means the mass was halved, right? 28 divided by 2 equals 14, right? If you divide 28 by 2, this comes out to be 14. Now 28 divided by 2 becomes 14. Now why are we dividing it by 2? Just by looking at the numbers, it's 14 and the mass of the silicon is 28. Then this species has to be silicon with a charge of 2 plus. This species has to be silicon with a charge of 2 plus, having a mass of 28. Because when you have a mass of 28 and a charge of 2 plus, the mass divided by charge ratio will be 28 divided by 2. If it is 28 divided by 2, it comes out to be 14, right? So that is what is asked here, what was asked here. So this would be our answer. This would be a final answer. So they were asking the question asked to deduce the formula of this particle. So since it says deduce, you don't need to show any working. You can just simply write the answer. That is fine. You don't need to write all these, I just wrote this for clarifying or explaining the concept. Okay, we move on to the next question. The next question would be 17B. 17B, draw a label 3D structure of graphite showing two layers of at least 13 carbon atoms each and the forces between layers. So you have to show at least two layers, and graphite has hexagonal layers in it, right? So what you do is you draw a hexagon first. You try to draw a hexagon. It's not, yeah, you draw a hexagon. Then you draw another hexagon attached to this. And you should be careful when drawing. You should count the number of carbon atoms. It's still not 13. It says at least 13 carbon atoms. You can show more than 13. So what the number of carbon atoms that we have here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 only. We need 3 more. See, we add one more hexagon. I think it's 13 now. It's already 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13, right? So what you can do is you draw another layer. So that's the bare minimum that you can draw. You can't draw less than 13. Yeah? You can draw 13. You show another layer, and between the layers we show forces between the layers. You draw lines, or maybe it's better to draw dotted lines instead of solid lines to show the attractions of the bonding. What you can do is you can show dotted lines to show the forces between the layers. Yeah. And you must always label the forces. So these are the forces of attraction between the layers, right? So that's the answer. So you can show more hexagons, but it's not really necessary because they said at least 13. The 13 is fine. So you shouldn't waste time, drawing more and more layers. Drawing more and more layers is basically a waste of time here. Yeah? Now we move on to the next question. Is question number 18B1. 18B1 says the acidic derivative of tartaric acid contains 20.8% potassium, 25.5% carbon, 2.66% hydrogen by mass, and the rest is oxygen. You have to calculate the empirical formula. If you look at carbon, hydrogen, and oxygen, my bad, I deleted carbon, hydrogen, oxygen. The compound contains potassium, carbon, hydrogen, and oxygen. Yeah. Now potassium has the percentage 20.8. Carbon has the percentage of 25.5. Hydrogen is 2.66. And the percentage of oxygen can be found by subtracting all this percentage from 100. 100 minus 20.8 plus 25.5 plus 2.66. Right? So in order to find the empirical formula, what we need to do is we have to divide these percentages by the relative atomic masses, which is 39.1 for potassium, for carbon it's 12, for hydrogen it's 1. For oxygen, we divide it by 16. So if you divide them, for potassium we get 0.532, for carbon we get 2.13, for hydrogen we get 2.66, for oxygen we get 3.19. Then in order to find the empirical formula, you have to divide it by the smallest number. The smallest number is 0.532. So you divide all these numbers by the smallest number, which is 0.532, and you get 1 here, you get 4, you get 5, and you get 6 here. All right, so that would be the empirical formula. So the empirical formula will be potassium would be 1, carbon would be 4, hydrogen would be 5, and oxygen would be 6. So that's the final answer to question number B1. All right. Now we move on to question number B2. B2, it says the acidic derivative or tartaric acid can be represented by this formula. Okay. Equation for the neutralization of sodium hydrogen carbonate by HKA2 minus. Now the charge on the anion is -2, and there are two cations, H plus and K plus. So this would be the reaction between neutralization of sodium hydrogen carbonate by this particular compound. So this compound H plus K plus A2 minus reacts with sodium hydrogen carbonate. Now the sodium hydrogen carbonate, see, it's a base. It's a base and it's a metal carbonate. It's a metal hydrogen carbonate. And this is an acidic compound. It says it's an acidic derivative of tartaric acid, so it's an acidic compound. So when you have an acid reacting with a carbonate, it will give you salt water and carbon dioxide, right? So one of the products of this reaction will be carbon dioxide. Another product will be water, because whenever you react an acid with a carbonate or a metal or a hydrogen carbonate, you always get carbon dioxide and water. So you will get carbon dioxide and water. And then you find the formula of the salt, right? Now the formula of the salt will have, see this particular acidic compound had H plus. So this H plus will get neutralized, right? There won't be any H plus anymore, right? If you remove the H plus, you are left with potassium and A2 minus. Now the A2 minus has a charge of -2. Now the potassium has a charge of +1. And there's another cation you are reacting with, which is sodium. So the formula of the salt would contain sodium, will contain potassium, and will contain the anion A2 minus. Because the charge of the anion is -2. So the charge of the cation also needs to be +2. The charge of the anion is -2, so the charge of the cation should also be +2. So this sodium forms a salt with the remaining species, right? And this equation is already balanced. You don't need to balance anymore. All right. Okay, now we move on to the next question. It says calculate the maximum volume of carbon dioxide gas released by the neutralization reaction in B2 from 5 grams of the baking powder in an oven at 190 degrees at 101,000 pascals. So what we would do is we would use the formula, the ideal gas equation, which is PV equals to nRT, right? We'd use this formula. Before we use this formula, it says it was made from 5 grams of baking powder. Now it says 5 grams of baking powder contains only 30 grams of sodium hydrogen carbonate by mass, right? Okay. So it says the neutralization reaction in B2, right? This is also the neutralization reaction in B2. So the mole ratio here is 1:1. All of these have the mole ratio 1:1, right? So initially we need to find the mass of sodium hydrogen carbonate. Mass of sodium hydrogen carbonate. See, it is sodium hydrogen carbonate is only 30% of the baking powder. So the baking powder has a mass of 5 grams. So the mass of sodium hydrogen carbonate will be 30% of 5 grams. 30% of the 5 grams is 1.5 grams. So the 1.5 is the mass of sodium hydrogen carbonate. Then what we do is we calculate the moles of sodium hydrogen carbonate, which will be equals to 1.5 divided by the molar mass of sodium hydrogen carbonate. The relative molecular mass of sodium hydrogen carbonate is 84 if you calculate, and this is found to be 0.017857, right? This is the number of moles of sodium hydrogen carbonate, which is equals to the moles of carbon dioxide. Because sodium hydrogen carbonate and carbon dioxide, they have a mole ratio of 1:1. Sodium hydrogen carbonate and carbon dioxide, they have a mole ratio of 1:1, right? So now we use the formula, the ideal gas equation, PV equals to nRT. The pressure would be 101,000 multiplied by volume. We need to find out the volume, equals the n is the number of moles, which is 0.017857 multiplied by R is 8.31. R has a value of 8.31 multiplied by temperature. The temperature is 190. You have to convert the temperature into Kelvin by adding 190 to 273. Then you find the volume, and when you find the volume is always found in cubic meters. So your answer would be 6.80256 into 10 to the power minus 4 cubic meters. But the question asks to find the answer in cubic centimeters, right? Now 1 cubic meter equals 10 to the power 6 cubic centimeters. Okay. So in order to find the answer in cubic centimeter, you have to multiply the final answer by 10 to the power 6, and when you multiply this by 10 to the power 6, you end up getting 680 cubic centimeters. That would be your final answer. All right. Okay, move on to the next question. It says we have to find the decrease in the volume. Decrease in volume in the carbon dioxide gas is cooled to 20 degrees Celsius. So what we do is we find another volume using the same formula, PV equals to nRT. Now the temperature is less. We have the same pressure. What was the pressure? 101,000. We find another volume. We use the same number of moles. What was the mole? 0.017857, 0.017857 times 8.31 times the new temperature is 20 degrees. So the temperature would be 20 plus 273, because we have to convert it into Kelvin. You find the volume. The volume comes out to be 4.3 into 10 to the power minus 4. The answer would always come in cubic meters. You have to convert it into cubic centimeter by multiplying by 10 to the power 6. So you get 430 cm cube. This is the new volume. So they have asked to find the decrease in volume. So therefore, decrease in volume will be equal to, the previous volume was 680. So you subtract 430. So the decrease in volume will be 250 cubic centimeters. I hope I could answer the question. Yeah. Let's see if there's any more questions to solve. in this paper. Yeah, there's another question. It says to determine the average number of carbon double bonds per molecule of the unknown sample to two significant figures using the graph. If you use the graph, you have to find the number of double bonds. Let me look at the graph. If we don't plot the graph, okay. From the graph, basically from the graph, you have to use the mean volume. Yeah, I think the mean volume that you have calculated here, the mean volume is found to be 35.7 cubic centimeters, right? So this is the mean volume that is found here, which is 35.7 cubic centimeters. So you have to determine the average number of double bonds per molecule of the unknown sample to 2SF using the graph. Now the graph that you have plotted, or that we are supposed to plot, this graph is volume versus the average number of double bonds, right? So in the y-axis you have volume, and in the x-axis you have the average number of carbon-carbon double bonds, right? So the graph that you get, just a generalized, I'm just sketching the graph instead of plotting, just to save time. So the graph looks like this. It's a straight line that passes through the origin. This is how the graphs look like. This is how this particular graph looks like. What you are supposed to do here, in order to find the average number of carbon-carbon double bond, so you have to go to the mean value of the bromine water, which is 35.7. So on the graph, what you do is you go to 35.7, maybe 35. Just an approximate guess here. Maybe 35.7 is here. So you go to the line and you find the corresponding carbon-carbon double bond. That will be our answer. And they have said to give the answer to 2SF. And the correct answer here, if you plot the graph and if you figure out the answer from the graph, the answer is found to be 1.2 or 1.3. This could be your answer. In 2SF, these two are the correct answer. You can write any one of the answers. Alright. Then we move on to the next question. No more questions to solve. Okay. Thank you.